In the first session, I'm going to tell you a little bit about the practical that you are going to do next week, Monday and Tuesday. And in the second session, we are going to have a sort of a break then. And in the second session, we are going to talk about the data that hopefully you will get and how we can analyze data. And I'm fully aware many of these things you have done at A-level or, well, GCSE or something like that. Nevertheless, there are hopefully a few things that are new to you. For example, how to construct a box and whisker plot. Have you done that? Who has done it? Hands up. Okay, so you know what an IQR is? IQR, yeah? Okay, good. So, okay, fine, we'll do that. But before we go into detail, let's talk a little bit about the practical on Monday, Tuesday. And basically, the topic of this practical is really molarity, dilutions, and precision. And that's the last topic, this precision thing. That is what we are going to do when we talk about data analysis. Okay, so what are you going to do? I don't know whether people had a look already at these things. It is, in my opinion, a fairly straightforward practical. And the first exercise that you are going to do is you just simply pipette some water. Why? Well, first of all, pipetting is the bread and butter of any bioscientist. If you can't do pipetting, then you are basically effed. And you need to be confident with that, because if you can't be confident about your pipetting skills, you can't be confident about anything. And also, in this practical, the aim is to then get some data, which you can basically play around and analyze. So what do you have to do? In the first place, you are using just simply plastic test tubes. These are these 4 milliliter plastic test tubes. You pick 9 tubes. So 3 sets of 3. A1, A2, A3, B1, B2, B3. That was not a 3. And C1, C2, C3. Oh, by the way, can you all hear me? Yeah? Okay, good. Just checking. And what you do is in the first, in the A series, you pipette some water in the B series, and in the C series, you put a different amount of water in. But before you do that, what you need to do is you weigh your empty tubes. Right? Weigh the empty tubes, label it A1, A2, A3. A permanent marker pen might be useful. Label the tubes, weigh them. Then, in the A tubes, you add 1 milliliter of water. Once you've done it, weigh them again. And of course, you write down the weights. Empty tube with water. In the B tubes, you add 2 milliliters, is that right? Yeah. 2 mil, 2 mil, 2 mil. And in the C tubes, it's 3 mil each. And once you've added the water, weigh them. So for each tube, you have A with water, and you have A without water. And you just measure how much water have you put in. So you subtract the weight of with water minus A without water, and this gives you how much water amount of water that you've put in. Ideally, since you use 3 times 1 milliliter, ideally for the A tubes, how much does 1 milliliter of water weigh? Loud? 1 gram. So ideally what you should get in an ideal world is that this difference with and without water is 1 gram. Will this ever happen? Probably not, because our balances are quite sensitive. So it could be that you measure 1.01 gram, 1.02 grams, and 1.00 gram. Yeah? But that's not a problem as long as we are in the right direction with the whole thing. So that should be absolutely fine. We're talking about precision a little bit later on. So that's your first task. What you then want to do is you want to present your data that you have in ideally a table and also as a sort of a graph. So, for example, conventionally what we do is when we draw a graph, on the x-axis we plot the thing that is under our control, that we can change. So we would plot here milliliter. So 1, 2, 3 milliliter. And on the y-axis, we plot what we measure. So that would be grams. 1, 2, 3. And hopefully, we will see a sort of a linear relationship. So this hopefully looks like this. Something like that. Yeah? And that indicates that the more milliliters you use, the more grams you have in your test tube. Does that make sense? Pretty much. You've got a straight line with 3 points. You might discover that not all of your points are directly on the straight line. So at one point in one of the next lectures, we will discuss what you do when the points are not on straight lines. We would have to use the line of best fit for that, and I'll show you how you can do that. So at least it looks reasonable. Task is clear, yeah? You do the same thing again, but this time not with these large 4 milliliter plastic tubes. You do that with smaller volumes and with the automatic pipettes, you know, the thingy bits. In the first case, you do that with the graduate pipettes and the suction ball. In the second case, what you do is you use what is called Eppendorf Tubes, or lovingly known as Eppies. These are little plastic containers about the size of my thumb. And usually they hold 1.5 milliliter. They have a conical bottom. Something like that. It looks more like a loo. Let me get this nice. Yeah, that's better. And they've got a lid, which you can just simply snap on. These are these Eppendorf tubes. And again, you use A1, A2, A3, B1, B2, B3. You measure them empty, how much they weigh. And you add a certain amount of water. Let me check how much water you add. Yes, you add 0.2 milliliter to A, 0.4 milliliter to B, and 1 milliliter to the C tubes. You use these P1000 automatic pipettes. Can anyone remember what the color of the pipette tip is for 1000? It's blue, exactly. Yep. And again, you measure the weight, and you will again plot this graph. So 0.2, 0.4, and 1 milliliter. And hopefully we will get a straight line. If you don't get a straight line, then obviously something interesting happens. And we then can discuss what's going wrong in this case. But let's not worry too much. I have fullest confidence in you that you will get straight lines. By the way, for the practical, you don't have to do a complicated write-up. You can, you would use your blue lab book to record the results, to do the table, to do the straight line, but you don't have to submit anything, right? Because I'm a nice person, just for once. Okay, does that make sense? Anyone questions? God, I'm good. Okay, so that's the first experiment. The second experiment, let's see if I find the right one. Nope, that's not. Yep. In the second experiment, you have to do a little bit of dilution. And again, you have to use your pipettes. And in this case, we don't use, as a tool, we don't use a balance. What we use is a different tool to actually measure the concentration of something. And we will go into more detail how you measure concentrations in one of the next lectures next week. We use a fairly sophisticated machine, which is called a spectrophotometer. People have worked with spectrophotometers before, haven't you? Has anyone worked with specs? Hands up. 1, 2, 3, a few people. Actually, what a spectrophotometer is sort of, it's a light bulb and a photodetector. Now you can imagine if you have a light bulb and there is something in between the light path that the photodetector will not be as bright as without the thing in it. Yeah? And these spectrophotometers actually allow to produce a specific wavelength. This wavelength or this light then will be absorbed by a certain compound that we use, and the light detector at the other side will detect less of the light. So this would look like a little bit like, here's the light bulb. It sends out the light, and here is the photodetector. And it measures, let's say, 100%. Now, if we do the same thing, light bulb, photodetector, but we put something in here that absorbs the light. Less light goes through, and the photodetector detects, let's say, 50%. And how much this is sort of, if you like, darkened, the photodetector, this depends on the concentration in this thing in here. Sorry. Just activated the wrist guard. I can't remember how to get rid of that. Never mind. It's my problem. We will discuss that in more detail next week, what's happening. Now, for our experiment that we are using here, we use a solution of this compound here, para-nitrophenol. Please be careful. It's slightly toxic, especially when you inject that straight into the brain, which I hope you won't. Treat it with respect. Health and safety rules apply, gloves, and so on and so forth. You probably want to even wear safety specs, because that is something that you don't want in your eye. And what you do then is you make a dilution of this compound. So, oh, for heaven's sake. We have a stock solution of 0.5 molar. That's our stock. And we want to prepare 3 milliliter of a 5 micromolar solution. 5 micromolar, 3 milliliter. Okay? So that's our stock. That's our working solution. You see what's coming next? Guess what's coming next? Loud. Say it.
Calculation.
A calculation. Over to you guys. How much of the stock solution do I actually need to get my 3 milliliter working solution? Over to you guys. Talk to people around you, convince them that you are right, but don't cough on them.
Are you going to ask me?
Sorry?
Are you going to ask me?
You? No. Because I know that you can do it, I think. Done it? Mm-hmm. So what was the equation for that? Yeah, loud? What was it? C1, yeah, exactly. So it's C1 V1 equals C2 V2. We say that's our, what do we do? That's our working solution. No, that's our stock solution. It doesn't matter which way around we do it. Stock solution, and that is our working solution. Basically, we want to know what is the volume of our stock solution. So what we do is V1 equals C2 V2 divided by C1. Now we said for our working solution, we want 5 micromolar times 3 milliliter, and for the stock solution we have 0.5 millimolar. Oh, bum! We have different units, eh? One is micromolar and the other one is millimolar. We can't really do anything with that. We can't cancel them out because, we would lose a factor of 1,000. So what we need to do is we need to convert milli into micro. Yeah? So we can say 0.5 millimolar. How many micromolar is that? 500. James. James said 500. Is he right? Is James right? 500 micromolar? Yes or yes? Okay, yes. I accept that. 500 micromolar. And now, things are easy. Life is good. We have 5 micromolar times 3 milliliter divided by 500 micromolar. Yeah? Now, I can also write this in a slightly different form. I can write this as 5 micromolar divided by 500 micromolar times 3 milliliter. It's exactly the same thing. Oh dear, I've offended somebody. Why do I write it like that? What is 5 divided by 500? Yeah, or simply it's 1%, or it's 1 over 100. Yeah, it's the same as 1 over 100. What happens to the micromolar? They cancel each other out, yeah, thank you. And this one here, this 100, 1 over 100, we also call this the dilution factor. Okay? So what we want to do is we want to dilute our stock solution, our paranitrophenol stock solution, 100 times. That's this 1 over 100. And the whole thing should give us 3 milliliter. How many milliliters do we need? Lisa, loud? 0.03. So we need basically 0.03 milliliter of this working solution, of this stock solution. How many microliters is that? How many microliters? 30, absolutely right. So that is 30 microliters. So we need 30 microliters of our stock solution. How much of the stuff that we diluted with, how much do we need for that to get 3 milliliters?
I was close.
You were close, yeah? Yeah, good boy. Do you want to sign the register?
Yes.
Tell him.
Oh, yeah.
You want to go, Ty?
Huh?
Do you want to go again?
Let go? That way?
Yeah?
No, I came.
I jumped. Good for you. Okay, so 30 microliter. How much do we need of the other substance in order to make it up to 3 milliliters? (2,970 microliter of, in this case, we use a substance, it's called a buffer. And we will discuss what a buffer does in one of the future lectures. So don't worry about it. At the moment, just simply accept we need something that's a buffer. So this is basically what you do. You make your I've got a problem here. Bear with me. We're back in business. So, what you do is you make your working solution. You make that up, 3 milliliters. Three times. Okay, so you've got 3 tubes with 3 milliliters of this substance. Then you use this spectrophotometer, and what you do is you put your 3 milliliters of the substance into a little receptacle. This receptacle is called a cuvette. It's a cuvette, not a baguette. Last year somebody called it a baguette. And everybody else started salivating because it was around lunchtime. It wasn't good. So that's a cuvette. What is this cuvette? A cuvette is just simply a plastic receptacle. that has a standardized format. Usually a cuvette has a blank side and it also has a side that is not blank. That looks a little bit like that. Now a cuvette, you can only touch on the non-blank side. Only touch on the non-blank side. Don't touch it on the blank side, on the clear side. Why is that? Because I told you, in the spectrophotometer, the light will go through this cuvette and it will be absorbed by the compound in here, so less light will go through. But the way it has to be is that the light can go through this cuvette, through the clear side. But your demonstrators will help you with that. And then the photodetector will tell you how much of the light is absorbed. Yeah? The background to that we do probably next week. One thing that you need to do in the first place is you have to sort of calibrate the spectrophotometer. And the way you do that, to calibrate a spectrophotometer, is you use what is called a blank. Or you zero it. How do you do that? Well, first of all, what you do is you take a cuvette, you add 3 milliliter, but only of the buffer. It's this bloody thing again here. Don't know how I get this. 3 milliliter only of buffer. So there is no nitrophenol in it. You put this blank into the spectrophotometer, and then you say, right, there shouldn't be any light absorbed because our absorbing substance isn't in there. There shouldn't be any light absorbed, so therefore I press the 0 button. And so that the spectrophotometer basically then shows 0.000. This means that no light is absorbed. Yeah, make sense? This process is actually called to zero the spec. You use it with a substance that doesn't absorb, and you tell the spec, right, measure it so that it doesn't absorb anything. So that's your second step. Your third step then is you use a cuvette. And this time you fill it with the 3 milliliter plus the para-nitrophenol. Shall we do the chemical structure? Anyone good at organic chemistry? So we have a phenol, which is an aromatic ring. We have a phenol, which means an ol. This is an OH group. And we have para-nitro. So the para position is opposite the phenol. And the nitro group is NO2. So that is what our paraphenol would look like. There's a little bit of artistic license in it, but I'm sure you'll forgive that. Okay? Now you put that into the cuvette. Don't press the 0 button at that point, and just simply check out the reading. So it might be 0.02. You record that reading, and you've prepared 3 working solutions, because I said you do that 3 times, preparing the working solution, and you measure all 3 working solutions. Yeah? Pretty straightforward, I'd say. Happy with that? You have done that with, what was it, 5 micromolar paranitrophenol. And you're also going to do that with, I think, 20 micromolar solution. Again, you have to calculate how much of your stock solution you need. So you want 3 milliliter of 20 micromolar, and you only have a 500 micromolar solution. That's your stock solution. How much do you need? Over to you. Calculation, please. Again, the trusted C1V1. Got that? 120 microliters? Yeah? Give yourself a pat if you got that. If you didn't, don't give yourself a pat. So 120 microliter, and you have to fill it up with water to get the 3 milliliter, and you do that 3 times, and measure that. Okay? Shouldn't take you too long. Any questions about that? Nah. Good stuff, hey? Well, I don't know whether it's good stuff, but... Lastly, let's see if I can find that. No, we had that. We had that. We are getting there. Lastly, we want to do the same thing with a protein sample. We use bovine serum albumin, which is a very standard protein. It's pretty cheap. And we do more or less exactly the same thing. This time, the light that we use to measure our substance actually is different from the first time. The first time we use light at a wavelength of around 400 nanometers. Anyone know what color 400 nanometers is, roughly? It's about yellowish color. This time, for the BSA, we use UV light. Ultraviolet light. And this ultraviolet light actually requires a different kind of cuvette. So your cuvette will be a plastic cuvette, but it's a special plastic, and it's indicated with a black dot. So only for this experiment, use the cuvette with a black dot, please. They are quite expensive because it's a special kind of plastic. And this particular kind of plastic actually allows UV light to go through. The normal plastic cuvettes won't allow that. It's a little bit like with glass. Normal window glass will not allow UV light to go through. So that's why you can't get a sunburn or suntan inside, even if the sun is going through the normal window, UV light will be blocked out. And in this case, we need this kind of cuvette because if the UV light is blocked out, then the whole experiment is basically pointless. And what we need to do again is 3 milliliters. You need to blank or zero your spectrophotometer. And you need to make your working solution. So we have a stock solution of 10 milligrams per milliliter. That's the stock. And we want 1 milligram per milliliter and 3 milliliters. How much do we need? So 1 milligram per milliliter times 3 milliliter divided by 10 milligrams per milliliter. And you see the beautiful thing, if you do it like that, the units cancel out. And we've got the right unit here. So this was a 1 in 10 of 3 milliliter. And that, of course, would be 0.3 milliliter. Or in microliters? 300, thank you. (300 microliters), yeah? And you make it up with water, or buffer in this case, to 3 milliliters, so you would need 2,700 microliter of the buffer. So that gives you 3 milliliters. Okay? And it also says you should make up another solution, which is a 1 in 50 dilution. So 1 in 50 dilution. How many would you use? Well, 1 in 50 of 300, of 3 milliliter. It's the same as 0.06 milliliter, and that is the same as microliters. Thank you, 60 microliters. And again, you do that 3 times for each of them. Or do you do it 3 times? I can't remember. I need to read the practical manual, but we will tell you then in the practical whether you do it 3 times or just once. And again, you measure the concentration. In your spectrophotometer, first you blank, and then you just simply put the cuvettes with the different concentration in the spec and take the reading. Okay? Happy with that? Okay, now here the big question. Can you do it? Bob the Builder. Barack Obama. Yes, we can. Right? Okay. Any questions about the practical? You have a few calculation questions then at the end, which you should attempt in the practical. If you've got any problems with that, let your demonstrator know, let us know, and we will help you with that. Okay? Happy? We have a short break, and then we talk about precision. If you know everything about precision, if you are from Switzerland and know about precision and, clockwork and things like that, don't worry, it is all recorded. Okay?